In technical training, the distance between recognizing a concept and being able to deploy it is often invisible. Scrolling through API documentation or reading architectural guidelines creates a comfortable feeling of fluency. The brain recognizes the terms and assumes it can execute the logic. But recognition is not mastery. Functional architecture requires navigating the friction of implementation, where missing logic and conflicting constraints immediately break the system. Breaking this illusion requires a mechanism called the readiness mirror. A rigorous certification exam, such as Anthropic's Claude Certified Architect Foundations, serves as an objective external boundary. It is a third-party check that evaluates performance with indifference to the candidate's internal self-image. To prepare for that specific threshold, we constructed an artifact, a 60,000-word, 12-chapter reference book detailing the production trade-offs of Claude's architecture. Architectural command is not something that can be verified internally. It must be reflected against an uncompromising external boundary. The primary mechanism of knowledge acquisition for this project is compression as comprehension. Reading source material lets the brain glide over blind spots. Writing forces raw information through a narrow structure, surfacing gaps in logic. Compressing a multi-domain curriculum into a single coherent structure is a constrained engineering problem. This compression acts as an automated gap detection system. If you attempt to connect context windows to subagent delegation and the logic fails, the structure flags the exact location of your ignorance. Complete understanding is not a prerequisite. The understanding is constructed during the physical execution of the artifact. The resulting 60,000-word book is a byproduct. It is the physical residue left behind by the gap detection process. Rote memorization attempts to store isolated facts for later recall. Active compression builds a relational map where every concept is structurally bound to the others. Producing a strictly formatted artifact converts raw documentation into dense, usable architectural logic. The text of this reference book was autonomously generated by an orchestrator driving Claude code. This is a literal application of the study material. To learn the system, we used the system to build the curriculum. This illustrates the agentic loop. An orchestrator sends a prompt, Claude returns tool calls, the execution layer runs them, and results feed back. A common failure is parsing natural language for task complete. The correct pattern relies on reading the typed stop_reason field. When the stop_reason field reads tool use, the loop executes tools and continues. When it returns end turn, the loop exits. This discrete binary path allows a text generation pipeline to run autonomously without intervention. Claude does not decide when to stop. The model generates responses, but the orchestrator layer owns the termination logic. The mechanics of stop-reason-driven termination were the subject of Chapter 1, and mastering them was the mechanical prerequisite for drafting Chapter 1. A single agentic loop drafting multiple technical domains quickly hits a wall. The context window fills with raw search results and tool call logs, eventually drowning the model in noise. This diagram shows the architectural solution, the hub-and-spoke multi-agent topology. Instead of drafting everything in one bloated session, a central coordinator dispatches discrete tasks. It dynamically spawns subagents, passing them only targeted, domain-specific parameters. These subagents do not share state. They do not pass intermediate reasoning logs back to the coordinator. The subagent absorbs the heavy exploration cost internally and returns a clean, structured finding to the center. This topology prevented the drafting pipeline from hallucinating cross-chapter scope. The agents lacked the context to confuse a chapter on prompt engineering with a chapter on CI/CD execution. Context isolation is the physical mechanism that allows an autonomous system to scale without collapsing under the weight of its own history. Probabilistic AI models treat system instructions as suggestions. This is a severe problem when generating a codebase that must follow strict repository formatting. This visual shows the configuration mechanism used to fix this, the CLAUDE.md hierarchy. As the generation pipeline moved through the repository, it loaded specific writing guidelines by concatenating global, project, and folder-level rules based on the directory. When prompt-based guidelines are insufficient, the architecture relies on hooks. This diagram shows an execution intercept layer. The pipeline utilized pre-tool use hooks to enforce absolute permission decisions before a file was touched, and post-tool use hooks to normalize data formatting before the model processed the result. Grounded. The technical vocabulary the curriculum tests is the exact vocabulary that governed the automated pipeline. The thing learned is the thing used. In software engineering, test-driven development dictates that you write the test evaluating a system's requirements before you write the code to satisfy them. This same engineering discipline can be applied to scholarship.
We can treat the published exam blueprint with its weighted domains and 6 recurring scenarios as a strict software specification. The generated reference book functions as the implementation code required to satisfy that specification. Learning becomes an iterative validation loop. You write the implementation, test it against the constraints of the exam blueprint, identify the failures, and rewrite until the output passes. This mirrors how a continuous integration pipeline blocks a deployment until all structural guarantees are met. Relying on this loop replaces the phrase, "I think I understand this," with "this output satisfies the specification." The same discipline required to ship working code produces a mental model that has been verified against the actual constraints of the system. Mastering a complex system requires externalizing your internal assumptions into a physical structure. Claude operates here as a collaborator, but its utility is defined by the precision of the architectural commands provided by the user. The final book is essentially a compiled binary. It is proof that the engineer's mental source code executes correctly. This artifact serves a dual function. First, it provides auditable proof of competence for the industry. Second, it provides the author with the evidence that their knowledge is genuine and complete. Avoiding the readiness mirror preserves the illusion of competence. Building against it forces the precision required for production systems. Architectural command is demonstrated when an engineer builds the very system that verifies the domain knowledge.